Alright, you made it through Integration Bootcamp. You know all the integration methods that there are, or at least all the ones that I can tell you about. Congratulations on that. Those things certainly can and do get ugly. But, of course, now comes the grand finale, because when you are reading a technical text and you have to solve an integral, well, nothing in the text will say, hey, use substitution, or hey, use integration by parts, and so on and so on. The real life situation, if there is such a thing in academia, is here's an integral, deal with it, solve it somehow. And so we need to have some kind of solution procedure, and the unfortunate thing is there really is no set procedure that says, okay, take your paper, take your pencil, start doing this, and you will get the solution in the following steps. So, well, we're going to talk about what we can do. There's some general advice. Really, the main thing, the main decision we can make is whether we want to do a substitution or an integration by parts. Sometimes we also have to do both, but then the staple of anybody who uses integrals in application is that people use tables. That is the old school approach. Now, of course, we can also use computer algebra systems, and we'll take a look at both of those. They're both rather user-friendly, and we'll be able to solve quite a few integrals with these methods at hand. Alright, so the big question is, which integration method do I use when? Well, that's a really good question, and there is no satisfactory answer. When you do homework in the section on substitution, you substitute. In the section on integration by parts, you integrate by parts. And on a test, nobody really tells you which method to use, right? So that's not fair, but we have to deal with it somehow. And not to mention then, of course, also the situation when you read, say, a physics text where you've got some kind of ugly integral that comes out of, I don't know, what things spit out really ugly integrals. Right now, the first thing that comes to mind is strange pieces in optics, for example. But those things, you just don't know how to solve them, and that brings me back to something that a fellow student of mine used to say, and that is, differentiation is technique. You give me a function, tell me to take the derivative, I can do it. The rules are there, you just have to be patient and hard-nosed and apply them. However, integration is art, because even though the rules are there, nothing really tells you which rules to use. So, when you integrate functions, one thing we just want to knock out right away, and that is whenever you are dealing with a rational function, unless you see something quickly, you just do the partial fraction decomposition. We've gone through that. It's technical, it's a lot of computation, but it's guaranteed to work. And basically, when partial fraction decompositions don't work, typically very little else works either. So that takes rational functions out of the picture completely. For everything else, therefore, you only have two methods left, integration by parts and integration by substitution, and you've got to decide between the two. And remember that there are two kinds of substitutions. There is the u substitution, u equals something, but there's also the substitution where x is equal to h of v. And sometimes you have to try both and decide whether substitution or integration by parts is better. Sometimes you even have to use both of them together, and then, of course, if worst comes to worst, you use an integral table or a computer algebra system. So, first example, well, compute the indefinite integral 6x minus 5 divided by 3x squared minus 5x plus 2. Now that's something, according to what we've just seen on the previous panel, this here is a rational function. Partial fraction decomposition, and you're done. However, sometimes you might be able to see something quickly, such as here, the derivative of the denominator is 6x minus 5. So, maybe a substitution can allow us to sidestep the integration by partial fraction decomposition. Set u equal to 3x squared minus 5x plus 2. That means du dx is 6x minus 5, and the derivative of plus 2 is 0. That gives us that dx is du over 6x minus 5. That means that the integral of this rational function is equal to the integral of 6x minus 5 divided by u, because the denominator is u, times dx, which is du over 6x minus 5. The 6x minus 5's cancel. We get the integral of 1 over u du. That's the logarithm of u absolute value plus c. We back substitute. That's the logarithm of 3x squared minus 5x plus 2 plus c. And basically now, if it's not this quick, use a partial fraction decomposition. So that should just take rational functions completely off the table. If you have a rational function, look at it to see if there's something obvious, and it really ought to be something that jumps out at you. If there isn't such a thing, do the partial fraction decomposition, and you'll get the antiderivative. However, then there are functions that are rather uncooperative, because when you want to compute the indefinite integral of x to the fifth e to the x cubed, well, let's see. To do a substitution, I would need to have something like a 3x squared in outside of the power, and I don't. To do an integration by parts, well, I don't know the antiderivative of e to the x cubed, and that's because I don't think that one has a pretty antiderivative. So you look at that pattern, well, I need an x squared. Okay, so 5 is 3 plus 2, so this is actually the same as the integral of x cubed times x squared e to the x cubed. And now you realize that we're going to do a substitution and an integration by parts together, right? For this one, we can find the antiderivative with a quick substitution, and this one, we can knock down the power by 1 using integration by parts. So we're going to differentiate this one and integrate this one, and so that means in integration by parts, you keep your u and you take your dv and find its antiderivative, and that's why I don't like the u dv stuff that people do in these formulas. There's a term that you differentiate, there's a term that you integrate. The term that you differentiate, you only differentiate at the end. First you keep it. Now we find the antiderivative here, and the antiderivative is 1/3 e to the x cubed. That's a u substitution, u equals x cubed, and that gives you that du dx is 3x squared, which means dx is du over 3x squared, and the cancellations give you the 1/3. And as I always say, when you read this, basically you can always double check by differentiating this term. When you differentiate that, you get 1/3 e to the x cubed times 3x squared, which is exactly the x squared e to the x cubed that we have here. Okay, now in integration by parts, we've got minus derivative of the one that we wanted to differentiate times the integral of the one that we wanted to integrate, so 3x squared times 1/3 e to the x cubed. The 3 and the 1/3, of course, cancel, so we can clean things up a bit. The stuff on the outside is 1/3 x cubed e to the x cubed minus 3 times 1/3 is 1. We keep x squared e to the x cubed. Well, we already know what that antiderivative is. That's 1/3 e to the x cubed. So we end up with 1/3 x cubed e to the x cubed minus 1/3 e to the x cubed plus c, and that already is the answer. And if you want to double check, you can do that by taking the derivative. So here's where we're also getting a few things together, where we realize that certain substitutions, you either do a side computation, there's nothing wrong with that, or if you can, the more you can do mentally correctly. Okay, don't try to do stuff mentally to impress yourself or to impress your teacher or anybody else, but if you can do it mentally and correctly, that means you are continuing to build your symbol manipulation capability to stronger and stronger levels, and that will allow you to ultimately not be worried about computations as much as if you wouldn't reach that level. On the other hand, if you just need to use a whole bunch of paper, well, look, I mean, we can do that too. So the idea ultimately is, of course, we want to get the right result. Okay, so what's next? Let's look at the indefinite integral of sine cubed of x dx. There are formulas for these things, but if something like this has to be computed very quickly, well, the integral of sine cubed of x dx, well, we know that that is the integral of sine squared x times sine x, and we know sine squared of x is 1 minus cosine squared x. Trigonometric Pythagoras is something that you just have to have down pat. And so this is the integral of 1 minus cosine squared x times sine x, which ends up being the integral of sine x minus the integral of cosine squared x sine of x. The integral of sine x is, of course, nothing but the negative cosine x, so that's not a problem. In the second integral, we do a u substitution. U equals cosine x. That means du dx is negative sine x, and then dx is du over negative sine x. And so the first integral, not just the antiderivative of the derivative of the sine, that's negative cosine of x, minus negative 1/3 cosine cubed of x, because as you do the substitution, all you have left with is a u squared. And then, or a negative u squared with a negative sign here. Antiderivative of u squared is 1/3 u cubed, and then you plug the u back in, so that's negative 1/3 cosine cubed of x. That's another one, either verified with a derivative or go ahead, paper and pencil, carry out that substitution. These pieces you can do, these are the kinds of things that are skipped in advanced texts, and you don't want that stuff to trip you up. So it's best to train yourself right away to fill in the gaps. And of course, there's got to be a plus c here at the end, and then if we clean that up, we get negative cosine x minus minus is plus, so plus 1/3 cosine cubed x plus c. And if you want to double check that, you can go ahead and take the derivative. Again, paper, pencil, work it out. It's not hard. Okay, so by the way, then, these integrals of powers of sines and cosines, there are reduction formulas for those things. I just want to flash those up. That's for mn greater or equal than 1. There's also a reduction formula for sine to the n. There's a reduction formula for cosine to the m by itself. And that's also for products of powers of tangent and secant, and so on and so on. Those things we can look up in tables, right? I mean, okay, if your teacher wants you to have them memorized by a test, then you just go ahead and do that. But that's typically something that even old school people would have said, look, you look that up in tables. So how do we work with tables? Well, let's look at trying to compute the indefinite integral of x square root 12 minus 4x minus x squared. Now that is horrible, and if we want to compute it directly, it would probably be a rather epic trigonometric substitution. How do you use a table? Well, you first of all open up the table, and then you make sure that you can still read what you're interested in, which is this thing up here. Well, okay, so now we go to the integral table, and here it is. Well, that's a little bit tiny right now, but let's take a look at this integral here. This is an x times, and the pattern in here is number minus x squared. We may have to complete the square, but this is number minus x squared. So in the integral table, we need to look for integrals that involve square root a squared minus x squared. Well, we've got those things here, and we've got them here with a plus. So let us take a look at how this continues after we complete the square. So here's the integral. How do you complete the square? Well, you keep what you have. Integral x square root of a whole bunch of stuff. And what do we have? We have a negative x squared. We've got a minus 4x, so that becomes negative x squared plus 4x. We've got the plus 12 here. The term that completes the square is half the square of the term in front of the x, so that would be 4 halves, 2 squared 4, so we add 4 and subtract 4. Then we do the algebra, and what do we have? We keep the integral, we keep the x, we keep the square root, we keep the negative sign. X squared plus 4x plus 4 is x plus 2 quantity squared, so that's got a negative sign here. Then we have minus 4 is plus 4, and 4 plus 12 is the 16. And so that is the integral of x times 4 squared minus x plus 2 quantity squared. So we're actually looking for integrals that involve square root a squared minus x squared. So now let's magnify that a bit so that we can see what we want to look at. And we're looking at something that is like an x times square root a squared minus x squared. Well, that's right there. So let's pull that up here. And, whoop, give me my book back there. Right, this is an x times the square root a squared minus x squared. Now there's a little bit of a trap here, and that is, here we have an x plus 2, so we're not quite done yet. The thing that we do with tables is we have to match exactly the pattern in the table, and this pattern doesn't have an x plus 2. Alright, so, well, we can turn an x into an x plus 2 by adding 2 and subtracting 2. Of course, that means now as we pull this apart, we get the integral of x plus 2 times our root minus 2 times the integral of 4 squared minus x plus 2 quantity squared. So now we've got two integrals, which unfortunately we have to have, but of course we also know the integral of square root a squared minus x squared because we have that right here. Now realize that the x here is an x plus 2 here, but that's a trivial u substitution, right? That's u equals x plus 2, and everything works out. So as we work this out, we would just have to replace everything that is an x here with an x plus 2, and everything that is an a with a 4. So let's see if we do that still on this panel. So now we use the table. Here is what we had, and here is what we are working out. Let's take the table and move it to a more convenient place. Well, I'll shrink it down some more. That's the kind of thing that you do in these presentations. So the first one is the integral x plus 2 square root 4 squared minus x plus 2 quantity squared. Well, the integral of x times square root a squared minus x squared is negative 1/3 a squared minus x squared to the 3/2, which would be negative 1/3. Our a is 4, so 4 squared minus, and wherever we had x, we go with an x plus 2, so minus x plus 2 squared, quantity squared, to the 3/2. And that's using this part of the table. And then we have the integral of 4 squared minus x plus 2 squared. Well, that's the integral of a squared minus x squared. So that one goes actually down there. Okay, I think I'll have to move the table around a little bit more. Or maybe I'll just shrink it here. Yeah, okay, we're getting a little squeezed, but it'll still work out because that way, in fact, we're focusing again exactly on what we want. This integral has a 2, so we get 2 big set of parentheses. Then what's the antiderivative? X over 2 is an x plus 2 over 2, because remember this is in terms of x plus 2. The a is 4, so we end up with square root a squared minus x squared, meaning square root 4 squared minus quantity x plus 2 squared. A squared over 2 is 4 squared over 2, and then we've got the arc sine of x plus 2 over 4. X was x plus 2, and the a is a 4. And then, of course, we put the plus c at the back, and I didn't even bother to simplify here. Of course, 4 squared is 16. You can do a little bit of algebra with that. But this basically is the antiderivative. And that's how you use tables. And then if in your application you need to have these terms simplified, then you'll have to use just some more rather ugly algebra with it. Okay, so last example. I want us to compute the indefinite integral of the 4th power of the cosine times the 7th power of the sine. And for goodness sakes, that's what you want to use a computer for, right? I mean, I've shown you those reduction formulas, and we can now just substitute into the formula, plug and chug at a very, very advanced level. But in the end, all we would need to do is, and again, I'll just want to show you that I'm not just messing with you, we are typing in what we've got, and what we've got is, let's pull that out of the way here. We've got cosine 4th x, that's cosine x quantity to the 4th. We've got sine to the 7th x, that's sine of x quantity to the 7th. Then we tell our computer algebra system to evaluate that symbolically. And that actually went faster than the first time around because it probably was stored internally. I did that in advance just to make sure that everything fits. If you scroll farther across here, the expression actually does end right here. And so the antiderivative of this thing is this expression. I'm not going to read it to you because, quite honestly, this expression speaks to you as much as it does to me, which is it speaks to me very little. The only thing we know is that this is the antiderivative, and so if we had needed this integral for some application, well, here's the antiderivative. We move on. And that's already it. So basically, as long as you are not allowed to use a table or a computer algebra system, the main decision is, after you've dismissed integration with partial fraction decomposition, you have to look at integration by parts versus integration with substitution. Sometimes you have to do them together, and certainly that is then something where you have to make a decision and where the pattern manipulation can get lengthy. However, this is good stuff in pattern recognition. When things get too ugly, even the old school people who taught me, especially in physics, would say, hey, use a table, okay? Because the people who taught me grew up without these symbolic computers, and in fact, when I was in school, symbolic capabilities of computers weren't that great yet, so a computer algebra system wasn't quite an option yet. And then, of course, modern day, if you just need the answer, and that in many jobs is what you need. I mean, the reason why I get paid to tell people that the integral of the cosine of x is the sine of x is because I teach integration. If I was an engineer, I wouldn't get paid for a computation where I say the integral of the cosine of x is the sine x. If I was an engineer or a physicist and I'm just interested in the answer, well, I would stick it into a computer algebra system just like anybody else. The main thing, and that's what I've been also harping upon all along, is we've taught you here a reading skill, and that reading skill is best further fortified by also making you write it out, by making you solve those integrals, so that when you are in a physics class, when you are in an engineering class, when you are in a physical chemistry class or something like that, that as the computations are happening, you don't have to worry about whether the computation is right or wrong. You will have enough confidence and ability to realize that you can get these computations right. And once you have that, you can actually focus on what the computations mean. You can focus on what the symbols in the computations mean. And that is really where the theoretical science gets exciting. When those symbols speak to you, when those symbols can actually tell you something about how nature behaves. But before we can get there, we have to make sure that the symbols don't trip us up. And that's what we've done here. Now get to it. When I tell you to solve an integral without a table and without a computer algebra system, do it like that. When I tell you use a table, go ahead and use a table just to make sure that we'll be okay in the future. And that's now really it for Integration Bootcamp. You've made it through the past stage, or well, through the first half of the last stage, because now it's up to you to solve some integrals. Get to it.